Our first presentation is by me, Dr. Sudhanshu Panda. I'm from University of North Georgia. As you see, my topic of presentation is remote reach water quality assessment with geospatial data. So let me quickly go over this presentation, then we'll start the second presentation in time. Anyway, guys, check that the presentation is about remote reach water quality assessment with geospatial data. By now, you know that most of my work deals with geospatial technology, GIS, remote sensing, GPS, and information technology. And as I told again and again, that geospatial technology makes any kind of environmental management much efficient, quick, and accurate. And my co-authors in this study, Mr. Andrew Allison, he is my student, he just graduated, and Dr. Amatya, he is a research hydrologist at Center for National Forested Wetland Research Center, USDA Forestry Service in South Carolina. And if you guys, some of you are not conversant with the term reach in United States perspective to the environment, reach means streams here. It is in India and other places, reach means to reach somewhere, but reach here is like creeks or streams or water bodies, okay? So introduction, the Federal Water Pollution Control Act, which was passed in 1972 in United States. So the objective of the act is to restore and maintain the US water quality, chemical, physical, and biological integrity of the nation's water body by preventing point and non-point sources going into the water bodies. So if you do not know what is point and non-point, point sources are the direct pollutant going to the streams, which we know exactly how much we are getting, like from, say, city stormwater locations or maybe some factories. So those are. And your non-point source, which we cannot really know exactly how much, where it is going, those are mostly from the agricultural land or the forest land. You apply fertilizers or pesticides, they washed with your runoff and they go there. And the number 2 point, United States has a like scheme called Total Maximum Daily Load, TMDL scheme. TMDL means it allows a maximum amount of pollutant that a body of water can receive while still meeting water quality needs. So, please. So like there is a limitation of the amount of phosphorus, nitrogen, other pollutants in water. If that amount exceeds in the water, then it is called impaired stream. And that is done through TMDL. And to meet the TMDL standards, most of the counties, cities, and states monitor the water quality of their rivers like on regular basis. Like they have their environmental department, they go take samples out from the streams, rivers, and test it in the lab. They found out actually how much amount of E. coli, fecal coliform, nitrogen, phosphorus, turbidity, all kind of stuff is there. So if they cross the limit of the TMDL, then it is considered impaired. And then everybody knows that, they will find a way to make the water body cleaner again. So however, the regular in situ water quality monitoring is very expensive and very time consuming. If you go to stream, take the sample out, then test it in the lab, it takes a longer time and it is costly. So that is the reason geospatial technology, which is GIS, remote sensing, GPS, information technology, is a proven technology we already know, and it makes environmental modeling and monitoring very efficient, economic, accurate due to its better understanding of the spatial nature of the your environment. So use of geospatial technology is one of the best tools to develop water quality prediction models by studying the watershed environmental dynamics. What does it mean? Like when you go to a location to sample water, the water is actually coming from a larger area. So that is called the watershed. So to that point, from different land cover, land use, water flows. So if we know that dynamic, like how much forest cover is there, how much your urban land is there inside that watershed, what type of soil is there, what is the slope of the land there, if we know them well, we can analyze them to find out how much is contributing through those watershed land. And only geospatial technology like remote sensing, GIS can understand that spatially very well, and you can model it easily also. Objective of the study, to develop algorithms using watershed-based land use data and soil characteristics to estimate various water quality parameters values to support TMDL analysis. That means we will be a kind of a good tool for TMDL analysis. Using GIS remote sensing data, which is free, we can analyze and tell that looks like this particular part of the stream or reach is impaired. So they can go take samples and test it and confirm it. Otherwise, blindly just going everywhere and finding out no impairment, it costs a lot of money. So that's the reason this technology, this study is actually to help that. Methodology, this is the, so this one is your Georgia, this is my whole county where I live, and Gainesville city is here. So this is part of the Gainesville city. You see this, these are roads, white areas are buildings, and the grass areas are kind of, these are forest, dark black area or dark green area, and these are grass. So this is the watershed we are studying. And this is the urban watershed, and the data and software we used in this analysis, we have 2-feet resolution DEM developed from LiDAR data of the same resolution. LiDAR data, you guys know, those are images taken from aeroplanes with laser, and those can tell you exactly what is the height of your trees, what is the height of the buildings, what is the elevation of your land, all these things. So digital elevation model is created from that. And we have stream data, we have land use data. Important part here, we have 5 years of land use data, 2005, 2006, 2009, 10 and 13. Because we need to check how the land cover is changing and how that land cover change is impacting the water quality. And we have water quality data collected, I have it later, in situ water quality data collected all these years. When these images are taken, water quality data are collected by Gainesville City Environmental Department. We got those data from them. Then we have Sorgo soil data, which is high resolution soil quality data. We have ArcGIS software to work with. This is a free soil and water assessment tool you can download from this website. So ArcSWAT watershed modeling software. We have SPSS statistics software, and also you will be amazed, Microsoft Excel you guys all have, you do not know it has a statistical package, one of the quality statistical package. And here I will show that tool pack MX Excel you can use as an add-in and do a moderate kind of statistical analysis in that. And I will go quick now. These are the data. This is your DEM. We have used 2 watersheds, sub-watershed 1, sub-watershed 3. So, but the sampling points, water samples collected by Gainesville City is around 12 locations. But those are close to each other, so that watershed will be smaller. So that's the reason we didn't go with everyone. We'll later try to use all, not all, maybe around 6 or 7 watersheds. Now we use only 2 watersheds. You can check the elevation from here, and this one is the soil data for 2, Sorgo soil data for 2 sub-watersheds. You can check these are the sampling points where the Gainesville City Environmental Department samples. But we use this guy and this guy as our sampling locations, so it creates 2 watersheds. And this is other, like you have the roads, you have the pipes, you have like streams, all kind of other GIS data part of it. The pipe means those are like your point source. They directly send pollutant to the water. They got license for it. This is another very advanced technology to use SWAT software to delineate those watersheds. You saw those watershed boundary. These are delineated using the DEM. This is the step-by-step procedure. The bottom part is to do the model. And here is the procedure. Whatever the land use data we got NAP. NAP is called National Agricultural Imagery Program data. It is 1 meter resolution data. It is government pays for it to get those images every year in the crop season, and we get for free to analyze. So we downloaded this data. This is the procedure. Some of you want to know. This is very direct. To be honest, whenever I present anything, I do not keep anything in me. I just have my presentation. Anybody can just use it just like that. But most of the presentation you will see, lot of things are hidden, as if they don't want to give. If I do a work, anybody should follow my work. So this is step-by-step procedure. If anybody want to follow, they can follow it. And this just classify, this is the original image here. This is the original image following this procedure in ArcGIS. Isocluster, and we use your reclassified data and hybrid your isocluster and maximum likelihood classification, then you get those images. And we have 3 classes. We didn't go for many classes. 3 classes are grass, urban, and your forest. This is the final model for our entire work. I do not dwell on this, but it is a straightforward, and this entire work is automated. Somebody can just, these blue things are the original GIS data or input data. The green are like created data by our model, all the greens. And the yellow ones are the tools available with ArcGIS software. So at the end, we got our result. And the results I'll show you. And here, what we did, we classify all 5 years of images and find out the percentage of the land cover. Percentage means the 3 land covers we had, urban, how much percentage from watershed 1, how much percentage grass in watershed 1, how much percentage of your forest in watershed 1. The same way for watershed 2. And we know from that watershed, water is flowing to the exit point where the water samples are collected, they are tested. And we have the nitrogen, phosphorus, all kind of data there. And here is an example how you get the percentage from it. And also we have the soil data. We use the soil MUID, so map unit ID, that tells us exactly what type of soil available there. And this is the 5 different type of soil we had, 5 different type of soils. And then finally, once we make a table of percentage of all land uses of that particular year for that watershed, and percentage of your soil types, and correlate that with different type of your particular time, particular watershed, what is the water quality data we have. I have a table I'll show you. And we had 14 total variables like pH, alkalinity, conductivity, phosphorus, all kind of stuff. And that is Y variable. And your X variable, which is independent variable, we get from images or your soil data. So those are percentage of land use types and percentage of soil texture types, 7 variables. So now you can see it here. This is the procedure regression we did in MX Excel. Like you go to Excel, to the properties, and in the properties you can select I want this add-in, the toolpack, VBA toolpack add-in. So if you get that, then you can data analysis tools show up. Then you can do all kind of statistical data analysis. You will be amazed how many are there. This is just with your there. You don't need a statistics software to do it. It does very advanced statistical analysis. And we use the regression to do it. You can do regression all kind of way. And regression results shows up as I will show you. So these are the results. We have 2 watersheds you saw there. And this is your 2005 NAP classification data. Number 1, the green color is forest, yellow color is grass, and number 3, red color is urban area. And it changed. If you check the image, it doesn't look like, but when you go for percentage, in one single year, it got changed. Because people cut forest, make a new house. So with 1 meter resolution, we get everything in detail. They are not same. This one is now 2009 classified image. This is 2010 classified image. And this is 2013 classified image. Then this is your soil data you saw earlier. Soil data does not change over a year because we do not do soil testing every year. We can do. And this is the final table. You saw that this is 2005, 2006, subwatershed 1, subwatershed 3, 2006, 2007. And these are the forest, grass, urban percentage. Yes. And your soil, different type of soil percentage, coverage percentage. And at the same date or same time, in the same watershed, these are your water quality data. This is dissolved oxygen, temperature, BOD, total suspended solid, total total solids, pH, then phosphorus, total kinetic nitrogen, ammonia nitrate, all these things are there. Fecal coliform, E. coli, these are tested. So we correlate those numbers with our percentage of land cover and soil to it. And you can check, these are the results. Check that this one, the turbidity didn't work that well and we found out of the 7 variables, only 3 variables really correlating. Other 4 variables are kind of not that great correlation there. So that's the reason we do not care about them much, and we know that why not, because those are very tiny amount in the watershed. So that's the reason the X variable is mostly your forest, and X variable 3 is your urban, and one type of soil that I will tell you later. So that 3 things are correlating well. And I have all the R-square check that your conductivity 92% very well predicted. So that means with land cover data and soil data, we can predict the conductivity of the water like with 90% accuracy. And this is your pH data. It predicts really well, 82%. This one doesn't work that nicely. You can check the second R-square, 82%. Then this one 90% alkalinity, R-square on the top left, second row. Then your DO, it works not that bad, 50%, but it's not that great. Your fecal coliform can be predicted with 55% accuracy. And that too, you saw that we have only 10 data. If we get more data, we could have a robust model. And my plan is to make it more robust. I started working with in Arkansas, so I'll show you later. And this is nitrate. This one is E. coli, predicted well, 64% prediction accuracy. And this is the example, what does it mean to you? Like we can develop an equation just like we have it, intercept plus X variable 1. This is the X variable here, X variable 1, X variable 3, and X variable 7. So that way we will develop the algorithm. Somebody can take that and plug in percentage of forest of their watershed, percentage of urban of their watershed, and percentage of Madison sandy clay loam which is available in our area. You could have different type of soil. Then that algorithm will give you exact that Y. Y value will be either turbidity or E. coli or whatever. So you can calculate them from there. So this is the software I developed while I was doing postdoc, and we are planning to modify it and make it better. You can see this is developed in Visual Basic. I'll give you a demo, quick demo. And this is the result you get. So what it does, if you have your percentage of or the acreage of your land use, and you know that after 5 years somebody caught already 100 acres of forest, they converted that one to say urban land. So you plug in number instead of say forest here 2441 acres, you can say 2241 acres. Then you add here residential cover was 0, you can say 200 acres of residential. Then you click in, it will automatically give you the amount of nitrogen phosphorus load extra will be there in the watershed. So this is the, I hope it will work. So this one is the demo of the software. Give me 1 more minute, okay?
What you got?
Okay. Yeah, it should come. It was working. If not, let me go here and so.
What is you trying to do?
There is a software I need to run. It's taking longer time.
It is stuck in processing. Okay.
Let's see.
Okay, close it. Yeah. It should come. It was working. Yeah.
Okay, there it goes.
No. Just went out.
Some files will be taken.
Yeah, see, check this. This is the software pollutant budget estimation form. Now, I go in here, say, if I put the same numbers, okay? Say, say 1405, that is the same amount of grass. Then say put maybe evergreen forest, we got another, somebody did the plantation, you got 100 acres of evergreen forest. And somebody cut the forest by 400 acres, so you got 2041 acres. Then somebody, now check that it is automatically converting to hectare, because some guys understand hectare. And now total fescue is a grass, say it was same 4116, okay. And this one is a 2947 mixed forest, we didn't change anything. So you can always change, and that 400 acres, we put that here in the residential cover. So 400, and now you click on open. So it is looking for a file. Say this is the data. Actually, I do not have the real data with me to work with, so it doesn't. I'll put some numbers here so you can see it. I'll say put, if I have the correct file, it will plug in the values over there, like total P, actual, total P, total N here. So let me plug in some numbers there. Say 1.5 and tab, say 200. Just some packing numbers I'm putting. Say 1.2. Give me just one more minute. Then 1.4. Then total sediment, say 110. Okay. So now you go here, calculate. So now this one shows up. You click on calculate. Total watershed does not match, it is same. So we need to check, 909. So I need to increase 500 here because I reduced 500 somewhere. So 900, okay. So now calculate. Yeah, still doesn't match. Huh? How much is coming? 509. Which one I missed? 2947, 4116, 400 I took out. Oh, it should be 300, okay. 1405, 900, 41, 41, 41, 41. Yeah, so matches with the area. So now click on, check that it automatically calculates for you sediment. Then you click on the graph, it will make a graph for you. It will tell you based on the actual, what was the actual, now how much change happens. And the same way, if you want to point source contribution, say change by 20%, change by 30%. Suppose I'll be changing by say 20%. And poultry litter application, I'll reduce by say 50%. And fertilizer application, I'll reduce by say 40%. Then click on submit, it will tell you how much. The red color means it is still having too much load there. So that way you get. So this is the one we already developed and we'll modify it to make it better. Let me finish. And conclusion, through this study, the algorithms developed as I told can be used for any watershed, or the procedure what we did, somebody can follow it and develop their own software instead of just in situ sampling collection and testing. They can just use remote sensing GIS data and know which river will be impaired or something. And this study will also support in US the TMDL team. They will be knowing beforehand which river they have to go and sample instead of going blindly everywhere, spending money and getting nothing. So this is all about, and I acknowledge the city of Gainesville. They provided us with the LiDAR-based DEM and also the in situ water quality sampling data. This is through my student, Jeremy Riley. He is now, he was working there and now working as an engineer over there. So thank you all guys.